derive relationship between the Young's modulus E, the shear modulus G and the Poisson ratio nu. From this different books follow different ways of deriving it, following from this book by Ugarel and Fenster, Advanced Strength and Applied Elasticity. Only for this part I have referred this book because it was in line with what we have discussed. Okay. First I will give an overview of what we are going to, how we are going to proceed. Take a two dimensional element, okay. It could be a plate or region inside a solid and subject to pure shear stress. Okay. So, it is subject to only shear stress, that is a point to be noted. The two dimensional element subjected to pure shear stress is shown here, and our usual sign convention is adopted, okay. On a positive phase positive force, and similarly on a positive phase positive force. So, all stress shear stress components are in the positive sense, okay. And negative phase negative direction of force, negative phase negative direction of force. What we are going to do is consider the diagonal and then derive expression for normal strain along the diagonal in two different ways and equate. What do we mean by that? When you apply this shear stress, that the diagonal elongates. So, which means there is a normal strain along the diagonal and we are going to derive expression for this normal strain in two different ways and equate it, that is the overall idea. Okay. For deriving the first relation, I would suggest you to recall these slides which I discussed earlier. I just shown here for a purpose of recall. We discussed this when we discussed the components of difference in displacement due to normal strain, shear strain and rotation. Our attention or our relevance right now is this case where the component where we discussed components of displacement because of shear strain only. Okay. So, just show the slides just for recall. We consider a plate subjected to only shear strain, okay. And in the case of shear strain these angles are same, okay. Earlier they were just alpha and beta, but when it is subjected to pure shear strain they become equal and they are just alpha, okay. And when we discuss what is the difference in displacement in x direction, y direction, etc. Okay. Okay. Now, as I told you, we consider a two dimensional element subject to pure shear stress, and pure shear stress results only in pure shear strain. That is the first statement. Pure shear stress, when I say pure shear stress, there are no normal stresses acting, only shear stress is acting, results only in pure shear strain. So, there is no normal strain, okay. Now, now normal strain along x and y axis, okay. We are considering only two dimensional case, okay. Now, if you look at the title of the slide and this pure shear strain, this it may look contradicting. Thus, title says normal strain along diagonal, first line says pure shear strain, okay. When we say pure shear strain, it means that there are no normal strain not along any direction along the x and y direction. So, when I say pure shear strain, I mean there is no normal strain along x and y axis, not along any direction. There can be normal strain along other directions. For example, there is normal strain along the diagonal, okay. That is the meaning of these statements, okay. Pure shear strain means no normal strain along x direction and y direction, can be along let us say the normal direction, and there is normal strain, okay. Okay. So, there is normal strain along the diagonal, okay. Okay, now, what is shown here? This diagram is similar to the diagram which we have seen earlier, the previous slide, the recall slide. The red boundary shows the initial state and subjected to pure shear stress and results in the final state given by the blue boundary. Okay. And as we have discussed earlier, it is symmetric and the angles, these two angles are same, they are both alpha, and so this angle is also alpha, this angle is also alpha. Now, the diagonal PQ becomes PQ dash. Okay. So, which means there is normal strain along the diagonal. Okay. Let us write an expression epsilon PQ, which is normal strain along PQ is equal to length of PQ dash minus length of PQ by length of PQ. Usual definition of normal strain, change in length by original length. What is the change in length? Length of PQ dash minus length of PQ divided by length of PQ. So, what is the change in length? Length QQ dash divided by length of PQ. Now, how to find length of QQ dash? For that, let us consider this triangle as we have discussed earlier also. When alpha is very small, so it can be approximated to a triangle. When you consider that triangle and take tan alpha as approximately equal to alpha, okay, then this side is alpha delta y. This is alpha, this angle is alpha and this length is delta y. So, when you consider tan alpha is equal to approximately equal to alpha, this side becomes alpha into delta y. Similarly, if you consider this triangle, once again tan alpha is approximately equal to alpha, then this side becomes alpha into delta x, this length is delta x. Okay. So, and this whatever is shown here is magnified and shown here. The increase in length QQ dash, that increased length is shown here, and the this length is the alpha delta x and this length is alpha delta y. Okay. Now, we can find out the length, the increase in length QQ dash is equal to, applying Pythagoras theorem, this is a right angle triangle. So, length of QQ dash is equal to square root of this length plus square of this length. Okay. So, square root of alpha delta y whole squared plus alpha delta x whole squared, and take out alpha squared, and then of course out of square root you get alpha, and what remains is square root of delta y squared plus delta x squared, which is nothing but the length of diagonal PQ, and alpha is gamma xy by 2, which you have seen in the recall slide. Okay. Okay. Now, what we want is length of QQ dash by PQ, that is what exactly we have derived here and bring to the left hand side. So, length of QQ dash by length of PQ is gamma xy by 2. Okay. So, physical significance of this statement is the normal strain along the diagonal is equal to the shear strain by 2, gamma xy by 2. Okay. Now, we will use Hooke's law. When I say Hooke's law, there are 6 equations, we are using one of the equations. What is that? Gamma x is equal to tau xy by g. So, epsilon PQ is equal to gamma xy by 2 is equal to tau xy by 2g. What we have related normal strain along the diagonal to the applied shear stress tau xy and the material property shear modulus g. So, we have derived one relationship for normal strain along the diagonal. Okay. We will have to derive an alternate relationship and equate both of them, okay, because normal we have a, let us say, a plate subject to shear stress, that normal strain should be same whatever way you look at it. we derive alternate expression and equate both of them. Okay. What is the second relationship? Now, we have a recall our discussion on stress element and then stress tensor. We represent the condition in terms of a stress element, okay, subject to only pure shear stress. So, in terms of a stress tensor, the diagonal components are 0. So, our stress tensor for this case is you have only tau x y and then tau x y, no normal stresses. Now, I want to consider a plane which is at an angle theta with the horizontal, okay, theta with the horizontal, okay, and I consider a vector along this plane, and that is the tangent vector to that particular plane, and which I denoted as S based on our usual nomenclature. And how do you, what is the vector? It is cos theta I plus sin theta j. So, cos theta I plus sin theta j represents the unit tangent vector to a plane. Because it is 2D, it looks like a line, but in general it is a plane. So, we have considered a plane at an angle theta with the x axis, and the you have a plane and the unit vector tangential to the plane is cos theta I plus sin theta j. Now, I consider a unit normal to the plane, which in our nomenclature unit normal vector, which in our nomenclature is n vector, and we know that this vector should be perpendicular to the tangent vector. So, what is the expression for this vector is minus sin theta I plus cos theta j. So, that when you take the dot product, it becomes 0. If you simply take a dot product n with s, you get minus cos theta sin theta plus cos theta sin theta going to 0. Okay. So, we know that normal vector should be perpendicular to the tangent vector. So, what is that we have done? We have represented the pure condition of pure shear stress in terms of a stress tensor, and wrote down expression for consider the plane at an angle theta with the x axis, wrote an expression for the tangent vector, an expression for the normal vector. Okay. Now, we will find the expression for stress vector. We have seen that it is the dot product of the unit normal vector with the stress tensor, or in simple terms matrix multiplication of the normal vector and the stress tensor, and the normal vector is minus sin theta cos theta in terms of we have written this in terms of matrix notation, and the stress tensor is of course given by 0 tau x y 0. A simple matrix multiplication will give us this vector tau x y cos theta I minus tau x y sin theta j. How do you do that? Minus sin theta into 0, that is 0, and then cos theta into tau x y will give you tau x y cos theta I. Similarly, the other component will give you minus tau x y sin theta j. Okay. Now, we will find out the, once we have found out the stress vector, we have already seen examples, we know how to find out what is the shear stress, what is the normal stress, etc., acting on the plane. So, let us find out what is the shear stress. What do you do? It is just the projection of the stress vector along the tangential direction. So, take a dot product of the stress vector with the unit tangent vector, okay. And this vector is from the previous line tau x y cos theta I minus tau x y sin theta j dotted with the unit tangent vector, which is cos theta I plus sin theta j. Do a simple dot product, okay. We get tau x y and then cos squared theta minus sin squared theta, okay. That is the expression for the shear stress. Okay. Now, I want to find out a plane where there is no shear stress, shear stress free plane. You will understand why do you do that. to find out that plane, what should I do? I should equate the shear stress to 0, and that is what I have done here. Shear stress which I have found out in the earlier line has been equated to 0. Now, tau xy cannot be 0 because we are applying that, it is a given constant value. So, what is the condition? That depends on theta. So, this tau ns becomes 0 for theta equal to 45 or theta equal to 135, and that is what is shown here. One theta is 45 is diagonal, okay. Theta 135 is this side which is perpendicular to the diagonal. Okay. So, theta 45 is this diagonal, theta 135 is this side perpendicular to the diagonal. That is why we are interested in a plane on which there is no shear stress, because remember where are we proceeding? We are going to proceed, we are proceeding towards getting another alternate expression for normal strain along diagonal. That is why we said we will identify a plane along which there is no shear stress. Okay. So, along this plane there is no shear stress, there is only a normal stress, and then on this plane also, which is 90 degrees, along that plane also there is no shear stress, there is only normal stress. Okay. Now, let us find out what are the normal stress values along those planes. How do you find normal stress? Just take dot product of the stress vector with the unit normal vector, and this expression for the stress vector dotted with the expression for unit normal vector. And if you take the dot product, you get minus 2 tau xy cos theta sin theta, which is minus tau xy sin 2 theta. Let us evaluate for the two planes. Theta 45 degree plane, you get tau nn equal to minus tau xy. Okay, this becomes 1, you get minus tau xy. For theta equal to 135, this becomes sin 2 theta becomes minus 1, you get tau xy, and that is what is shown here. Let me explain that. Now, this boundary represents the original stress element. Now, this represents the rotated stress element. Why rotated? Because we are one plane is along the diagonal, other plane is 90 degrees left of the diagonal. Okay. Now, we have considered this plane, and remember our tangent vector was like this and normal vector was like this. Now, we have found out the normal stress to be minus tau xy, which means it is acting along this direction. And now, because I am indicating the force on the other side, opposite side, I am indicating it in this direction. Remember we discussed, if we have a surface, the normal stress acting on opposite sides are equal in magnitude, opposite in direction. Okay. So, let me repeat, the tangent is this along this direction, normal is along this direction. We have found out the, for 45 degree plane, we found out the normal stress to be minus tau xy, which means it is along this direction. Now, this arrow represents the opposite side of the surface, and that is why it is in this direction. Okay. So, let me draw, tangent is this direction, unit normal is along this direction, the normal stress opposite to unit normal. So, it is along this direction, but the arrow is indicated on the opposite side of the surface. So, I am indicating this way. Okay. Of course, this we know is just the opposite side, okay, tau xy. Now, for 135 plane, 135 plane with theta is equal to 135, this is the unit normal, and we have found out tau nn is equal to tau xy, which means it is along the unit normal, and that is why this arrow is indicated this way, tau xy. Okay. So, what we have done is that we had a stress element subjected to pure shear stress. When you rotate it 45 degrees to the left, that is what we have done, rotate 45 degrees to the left, it is equivalent to a stress element subjected to only normal stresses. There are no shear stresses, that is what you see here. When you look at this dashed boundary which represents the rotated stress element, there are only normal stresses. those normal stresses have been expressed in terms of tau xy values, but in this rotated configuration there are only normal stresses and the new axis are denoted as x dash axis and y dash axis. Okay. So, along the x dash direction it is tensile and along the y dash axis it is compressive. Okay. That is what you see here, tau xy in this direction is tensile and in this direction tau xy is the normal stresses are compressive. Okay. So, original element subjected to pure shear stress, equivalent rotated element subjected to pure normal stresses. That is what we have done now. Why are we doing all this? Our final objective is to get an expression for normal strain along the diagonal. What is the axis now? X dash axis. Okay. That is what we will do now. Okay. The same figure is represented, I think now very clear to see here. In this rotated configuration there are only normal stresses acting on the sides. Okay. Now, we will apply Hooke's law in this rotated plane x dash y dash plane, okay, where only normal stresses are present, Okay. We will take remember we wrote 6 equations for Hooke's law. I am writing here one of the expressions for normal strain along x direction. This general expression epsilon xx is equal to 1 by E into tau xx minus nu into tau yy plus tau zz. We are considering 2 dimensional case. So, there is no tau zz. So, this is the simple expression for the present case. Now, we have to apply this along the x dash axis. So, normal strain along the diagonal. Now, the x dash axis and diagonal are coinciding along with each other. So, epsilon x dash is equal to 1 by E tau x dash minus nu tau y dash. Now, what is tau x dash is tau xy and what is tau y dash is minus tau xy, because it is compressive. Okay. That is what I have written here, tau x dash is tau xy and tau y dash is minus tau xy. I already have minus sign here and that becomes tau xy plus nu into tau xy. So, we can take out tau xy by E outside and write as 1 plus nu. So, we have got another expression for the normal strain along diagonal, a second relationship which once again remember relates to the applied pure shear stress and material properties nu and then Young's modulus. Okay. So, just to summarize this slide, first what we did was in the previous slide we had a stress element subjected to pure shear stress. We proved that is equivalent to a element which is rotated by 45 degrees subjected to pure normal stress. So, we considered that rotated element and applied the Hooke's law along x dash axis which coincides with the diagonal of the original element. And then applied the Hooke's law along that diagonal. Okay. So, now becomes very simple equating alternate relations for normal strain along diagonal. Okay. First we found out epsilon p q, the nomenclature was epsilon p q, but significance is same, normal strain along the diagonal is equal to tau x y by 2 g. Second time the nomenclature was epsilon x dash, physical significance is normal strain along diagonal. Though two different nomenclatures for the two relation, significance is same, normal strain along the diagonal. First time tau x y by 2 g, second time tau x y into 1 plus nu by E, both should be same. So, when you equate these two, you get the relationship as g is equal to E by 2 into 1 plus nu, and that is what we were proceeding towards. We wanted a relationship between E, G and nu, and they are not independent, the material properties are dependent. Just like to mention, we have derived this for a very specific condition, take a plate, 2-dimensional case subject to pure shear stress. But remember, these are relationship between material properties. So, they should be valid under any general condition. We can't take a very general condition, that becomes difficult. So, we took a very simplified geometry and derived the relationship, but they are valid for any condition since they are relationship between material properties. So, now we can write the Hooke's law in terms of two material properties. So, the first line represents the relationship between G, E and nu, which I derived in the last slide, and the 6 equations which I have written earlier are written here again. Okay. But now instead of G, I can write in terms of E and 1 plus nu. So, now these set of equations have only two material properties, which are E and nu. It is for us to replace any one material property in terms of the other two. Here I have replaced G in terms of E and nu. So, these set of equations have only two material properties, namely E and then nu. Okay.